Hello everyone, welcome to this video. In this video we'll be looking at the proof for the theorem which defines spectral family associated with an operator, right? So we'll be continuing with our proof. In the previous video we have proved the first part. Now we'll be proving second and third part in this video. This part has been done. So here we wanted to prove that whenever lambda is strictly less than m, where what is m? This is the lower bound of the closed interval in which all the eigenvalues or all the lambdas that lies, right? That resides. So here we wanted to prove that whenever we have lambda strictly less than this small m, then in that case the value of this projection operator E lambda, that is nothing but the zero operator, right? So this is what we wanted to prove here in the second part. In the third part we wanted to prove whenever lambda is greater than or equal to m, we wanted to prove that this projection operator is nothing but the identity operator. So let's move ahead and prove both of these parts. For the second part, again we are assuming all these results as such, right? These are the results which are obtained for the operators which are related to T lambda, which we have already studied. Okay, so in part 2 we wanted assume first of all that lambda is smaller than this small m, right? And we will be continuing our proof by the method of contradiction. So we will be assuming that E lambda is strictly not equal to the zero operator. In fact, we wanted to prove that E lambda is nothing but the zero operator. So let's proceed by the method of contradiction. So we'll be assuming the opposite. That means E lambda is strictly not equal to 0. If this is not a zero operator, that means it would give you some non-zero value at least for one z, right? So we assume that it is non-zero for some z, right? So we take that value to be x, that whenever we apply E lambda onto z, the value that we obtain is x, right? So we said this thing. Now we can see that E lambda of x, what is it? So when we apply E lambda onto x, so we could just substitute the value of x here. It is E lambda of z from here. So it would become E lambda square, right? E lambda square of z, and E lambda square is nothing but E lambda only. Why? Because it is E lambda that is a projection, and you know, being a projection, it is both self-adjoint as well as idempotent. So in this case we are using this property of idempotency. So here this E lambda square is equal to E lambda, and again this is E lambda z. What is this thing? This is nothing but your x. So you see E lambda x is nothing but x. So it acts as identity on the element x, which is non-zero. So we may assume that the norm of this element, that is 1. So we can do that quite easily. We may choose such an x such that the norm of that particular element is equal to 1. There is no issue in that. Okay, so next we wanted to make a contradiction here. For that, let's assume this inner product. Let's continue with this inner product T lambda E lambda x with x. Why we are taking this? Because we have certain result on T lambda E lambda, and we'll be seeing that in a moment. So let's consider the inner product of T lambda E lambda x with x, right? So you know what is E lambda x? We have just constructed this to be equal to x only. So let's substitute the value here. So this E lambda x, that is equal to x, right? So now you can open up this T lambda. It is T minus lambda I, right? So you could open up this inner product using the properties of inner product. So it is the inner product of Tx with x minus lambda, right? And obviously it is one such inner product. If you are taking out of the box of all the inner products, if you are taking certain random inner product, it would obviously be greater than the least among the inner products, which is nothing but the infimum of all the inner products, such that the norm of x is equal to 1. And in this case we are assuming the norm of x as equal to 1 only. So obviously this quantity is greater than the infimum, right? If that is so, you see what is this? This is the definition for small m. this is the lower bound for the given interval. So this is small m. And here this quantity x tilde, that just represent a notation. It just tell you that it is some general term where we are just defining the infimum over all the terms, right? So in this case, this is m minus lambda, and you know, we in the very starting we have assumed that lambda in our case is less than smaller this small m, right? So what would be m minus lambda? M minus lambda would be greater than 0. So this is what we are saying in this case, right? So overall, we started with this thing and we landed at greater than 0. So this thing is greater than 0. And what is this thing? It is the inner product of t lambda e lambda x with x. So if this inner product is greater than 0, that means the operator has to be a positive operator. T lambda e lambda has to be positive with whatever assumption we made, right? But this thing made give us a contradiction. Why? Because you know, t lambda e lambda, that is minus t lambda negative. Let me show you. It is minus t lambda negative, this quantity, right? So here in this case, this t lambda e lambda, that is minus t lambda, and you know, t lambda negative, that is a positive operator. So negative of t lambda negative, it is going to be a not positive operator. It is less than equal to the 0 operator. So in this case, we have a contradiction, because by the results that we already know, t lambda e lambda is less than the 0 operator, but we have made out a opposite thing. So this is a contradiction to our assumption that for certain z, this e lambda z is not equal to 0. So this thing is incorrect. If this is incorrect, so that means e lambda has to be 0 for every z, right? So this is what we wanted to make here in part 2. Similarly, we'll be proceeding for part 3 here. For part 3, let's see what do we have. Here we assume that lambda is greater than equal to m, and we will prove that e lambda is nothing but the identity operator. And again here in this case, we'll be going through by the by the method of contradiction. So in this case, we assume that lambda is greater than equal to m, right? Or we'll be first getting the result for lambda greater than m. For lambda equal to m, we'll be proving that part when we will be proving part 4, right? So for the time being, let's just talk about the case whenever your lambda is strictly greater than m. Okay. So in this case, we assume that lambda is strictly greater than m, and for that thing, let's proceed by the method of contradiction. E lambda is not equal to the identity operator. If that is so, that means I minus lambda e lambda, that should not be exactly equal to the 0 operator, right? If this is not exactly equal to the 0 operator, so that means there should exist some z such that whenever you apply I minus e lambda onto z, you should obtain some non-zero number, which is say x, right? And we consider the norm of that x to be equal to 1. Now we are saying when I apply I minus e lambda onto x, I am getting back x again. How this is so? Let's see. So if we wanted to see what is I minus e lambda of x, so let's just apply the value of x. Let's just substitute the value of x. You know, this x is equal to I minus e lambda of z. So let's substitute it here in this place. So we would have I minus e lambda square of z, right? This thing. So here we can open up this bracket or this square. So you have I minus e lambda multiplied with I minus e lambda. So you could just multiply the terms, you would obtain I minus 2 e lambda plus e lambda square, right, in terms of operators. So so that you can multiply this z inside. So you would have z minus 2 e lambda z plus e lambda square z, right? And you know, this e lambda square z, that is equal to e lambda only. Why? Because your operator e lambda, that is a projection, and it is both self-adjoint and idempotent. So in this case, because it is idempotent, this e lambda square is equal to e lambda. So let me substitute it here. So you could add and subtract these terms, so you could land up at this term, and you can again take out z, so you are having the term I minus e lambda. And what is this term I minus e lambda of z? That is nothing but x only. So you see, we started with I minus e lambda x. This is nothing but equal to x, right? So we have this thing. So now we wanted to get a contradiction here for this case. Again, we are assuming the inner product. So for this inner product, we wanted to have a contradiction. So let's see what do we have here. So we started with t lambda I minus e lambda x with x. Now you know what is the value of this quantity. This value is equal to x only. We have just made out this thing. So this thing is equal to x only, right? So let's substitute the value here, and then we can open up this t lambda. It is t minus lambda I. So this t lambda, that is equal to t minus lambda I. So let's substitute the value here. Then we can use the properties of inner product and open up the terms. Now this random term would obviously be smaller than the largest term, which is nothing but the supremum taken over all such inner products, such that the norm of such x is equal to 1. So here x tilde, that is a dummy variable, right? So you it is just a notation in order to tell you that we are taking the supremum over all the x which are present in the set, right? So and what is the supremum term? This is the definition for capital M, which is the upper bound of the given interval capital M. So we have this thing equal to m minus lambda, and in the very starting we assume that our lambda is strictly greater than m. So obviously in this case m minus lambda, that is less than 0 in this case, right? So we obtain a inequality here which tell us that this inner product t lambda I minus e lambda x with x, that is strictly less than 0. If this is less than 0, that means the corresponding operator, this one, has to be less than 0, right? So this is one result that we obtain using our assumption. Now let's see what actually is this operator. Is it really less than 0 operator, or is it something else? So in this case, t lambda I minus e lambda, this is equal to t lambda positive. Let me show you from the previous results. We have t lambda I minus e lambda, that is t lambda positive, right? And t lambda positive, that is a positive operator. So using these two results, our operator t lambda I minus e lambda, that is a positive operator. So from here we obtain that this is a positive operator, and by our calculation we obtain that this is a not positive operator. So we obtained a contradiction in this case. If so, that means whatever we have assumed is not true. We have assumed that e lambda is exactly not equal to the identity operator, so this thing is incorrect. If this is incorrect, so that means e lambda is equal to the identity operator whenever we have lambda greater than the capital M, which is the upper bound of the given interval. So this is the proof whenever we have lambda greater than m. For lambda exactly equal to m, we wanted to prove that again e lambda is equal to I. So this thing would be proved whenever we will be proving the next part. There in the next part we'll be proving the continuity of the given projection from the right. So that would give you em, where lambda is equal to m, the value is equal to I. So I hope you understood this theorem well, and the proof for part 2 and 3 well. We'll be talking about part 4 in the next video. Thank you for watching.